These next graphs are type of graphs called Euler circuits and paths were made famous by a city in Germany called Königsberg Bridge problem. And the current ruler of the day in the 1700s suggested if offering some prize money if you could find a path that would allow you to cross each bridge exactly once and no more. So, for example, if I started down there at the bottom and I came up and came across right here, and then maybe came over there, and then went to the right there, and I got to 6 of the 7 bridges, but I missed one. So let's try again. So maybe this time I'll start up here, and I'll go down through that bridge, and I'll come back up through that bridge. And again, I came really close. I got 6 of the 7 bridges, but I missed one again. So he set prize money up if you could come up with a path. A very similar problem to this is famous, is put in a lot of different brain teaser books, is you have a map you're looking at of 5 rooms with all these doorways, and you're trying to find a path in which you walk through each doorway exactly once. So maybe I'll start here and I'll try to maybe thread the outside first and see if I can come up with a path that cuts through every doorway exactly once. And I think I came close. I just missed that doorway right there. I got all but one doorway. So again, I missed one. So because of this, I missed. And because of this bridge, I missed. If you want, you can try it again, but Euler was the first one to sit down and actually say that he believed that it was impossible to do either one of these. He turned each of these maps into graphs, kind of like we've done before. So let's turn this into a map really quick. Let's call that region A, call that region B, that region C, and that region D. So in other words, he would call this a vertex A, and let's put B right here. Let's put C right there, and then let's put D over here. So he recreated this as a graph problem, kind of like we've made before. And so A has 2 bridges going to B, so we draw 2 lines from A to B, or 2 edges. And then A to D also has a bridge, B to D has a bridge, and B to C has 2 bridges, and then C to D has a bridge. So if you count really quick here, 1, 2, 3, 4, 5, 6, 7 bridges, or 7 edges in this case. And what Euler figured out is when he started to try to figure out that you wanted to basically traverse this graph, he would suggest that you have to basically cross over each edge once. Now to do that, think what would happen here. If I started at A, and I leave A, and I go into D, and I go out of D, and most of the vertices you're going to leave 2 edges behind, because you go into a vertex and go out of a vertex, you always leave 2 behind. You leave one coming in, one going out, so it's always going to be 2. So he figured that most of the vertices had to be even numbers, because as you went in and came out, you always left 2 degrees behind. And so if you looked at the degree pattern of this graph, like we talked about earlier, like the degree of vertex A is 3, the degree of vertex D is 3, the degree of vertex B is 5, and the degree of vertex C is 3, this one's going to become impossible because you're supposed to have a mostly even, if not all even, to basically make a traversable graph. So if you look at this next set, I gave you a couple to try just by playing around with. Like for example on this one, I know it's kind of hard to see on this graph paper, but they're asking, can you draw this graph without picking up your pencil? So let me see if I can do this really quick. I'll cover these up. So according to this, I think this person started right here at this bottom corner, and they went up. Let me make that a little bit bigger. So maybe I'll use blue. So they start by going up, and then going up to here. Now it's too big. Let me try one more time. Alright, so start down here, and then go up and down, and that looks like they went over to here, and then across here. I haven't picked up my pencil yet, nor have I crossed over the same line twice, and then back to here, and then down. I've successfully traversed that graph. I cover every edge exactly once without picking up my pen. Alright, let's try it again on this one. I think this one might be impossible. Euler suggests it had to do with the fact that you go in and out of vertex, so most of the vertices should have even degrees, and see, I missed on that one. And let's take a look at this one. Now, I started down here, and this one had a degree of 3. 1, 2, 3, 4. That had a degree of 4. Degree of 2. 1, 2, 3, 4. And that had a degree of 3. And that actually, we started here and we ended here. The only ones that can be odd are the ones you start or end at, because when you start there, you only leave one road or one edge behind as you traverse it. Every other edge must be even, because you always go in, come out, so you're always leaving 2 roads behind every time you cross through a vertex. So, small story to kind of clean this all up. What Euler figured out is to be an Euler path, which this one was, you should have 2 odds and the rest even. And that's exactly what I had there. I started at one odd and ended at the other odd. To have an Euler circuit, which means you're going to start and end at the same place, he determined that they have to have all even degree vertices. So that's why this one was impossible, because the degree of each vertex was actually 3. So according to Euler, and kind of showing what he came up with, they all have to be even, which would make it a circuit, or they have to have exactly 2 odds and the rest even. So let's see if this one the degree is 2, 1, 2, 3, 1, 2, 3, 1, 2, 3. So that one's not going to be possible because it has 4 odds. And if you look at the next one, it's basically 1, 2, 3, 4, 1, 2, 3, 4. This didn't show it very well on my paper. 1, 2, 1, 2, 3, 4, 2, 1, 2, 3, 4, 1, 2, 3, 4. So this one, it shouldn't matter where we start. It should work no matter what. So basically, let's try this next one. If they're all even, we should start and end wherever we started with. So if I start at M, and I trace out, and I go up, I go over, let's just make the entire rectangle first. And then I'll go up to P, and then down back to Q, and then I can go back up to O, and then back up to L, and over to N, and down to K, back to O, and sure enough, I was able to traverse the whole graph without crossing any line twice, and without picking up my pen. Alright, let's try to look at the degree pattern of this one over here. So the degree pattern of this next one, alright, W has 2, T is 3, S is 3, V is 4, U is 2, and R is 2. So again, this one's going to work because it's going to be a path that you're going to start at one odd and end at the other odd. So let's start at the bottom odd here. It really doesn't matter. You'll get there if you just start from one of the odds, and you should end at the other odd. So if I go over here to W, up to V, let's go back down to T, up to S, down to V, over to U, over to R, and back to S. Sure enough, I started at T and ended at S. So either all even or 2 odds. Let's try this next one. Alright, so on this one, beta is 1, 2, 3, 4, using some weird symbols. I think that's chi, 1, 2, 3, 4, it's like a big X. That's gamma. I think that's phi, that's a 2, 1, 2, 3, y is 3. I think that, it's hard to see if that's, I think that's delta, 1, 2, 3, 1, 2, 3, 2, and 2, so I think, and that's delta down there. This one's impossible because we have, basically we have 4 odds. Now if there's a line between these two, and I can't tell, on my paper it doesn't look like there's a line between X and Y, but on my paper it's 3's. If you have a line between these, that would make this 4 and 4, and then it would be possible. Now, let me count this one really quick. Alright, so in this one I just numbered them, so we have 2, 1, 2, 1, 2, 3, 4, 5, 2, 1, 2, 3, 4, 5. I'm just counting the number of edges that connect to each point. That's 2, 1, 2, 3, 4, 2, 1, 2, 3, 4, and 2. So this one should be possible. If it has exactly 2 odds, so if we start at one odd, we should end at the other odd. So it really doesn't matter. We'll start here at the bottom one. Let me go down, over, and back, then back to 1, and up to 4. It really doesn't matter the path. You just try not to block yourself in, and you should be able to start at the one odd and end at the other odd. I'm just tracing out until I cover the whole graph, and if I go down here and down and then back up, sure enough, I started at the bottom 5 and ended at the top 5. Alright, so a little bit more formally, let's try these problems down here. So this time I'm actually going to ask you to list the actual path or circuit. Alright, let me stop though, and I'll start again, and we'll do the next page together.